probably 3 or 4 of these this morning. It's not very difficult stuff. I'm not a huge fan of this first section, but it's kind of a nice way to start the year off. It's kind of a softball to start. All right. First thing we're looking at is there's 2 types of reasoning. And the first one we're going to look at is inductive reasoning. And the first thing we need to know is what a conjecture is. A conjecture is a statement or an unproven conclusion based on evidence. So in inductive reasoning, you do your own trial and error, and then you come up with a statement, a conjecture that says this is because of this. So for example, if I let's say I flip a coin. Let's say I flip a coin 25, no, let's do an even number, 20 times. How many times should it come up heads?
10.
How many? 10. So 50% of the time it should come up heads. Yes? But if you do the trial, maybe it comes up heads 12 out of the 20 times. So your conjecture might be, if I flip a coin 20 times, 60% of the time it's going to come up heads. So that's inductive reasoning. Okay? Deductive reasoning is using something that has already been proven to you to come up with a conjecture. So for example, what is the sum of all of the angles inside a triangle? 180 degrees. So you got that because somewhere along the way, somebody has proven that if you take the exterior angle and the interior angle and they add to 180, and then you take the exterior and the interior of the other two and they all add up, those 3 all have to add up to give you 180. So that is deductive reasoning. You're taking something that has already been proven to you and coming up with a conjecture. A conjecture, again, is just a statement on a theory you have based on the trials that you have run. Okay. Inductive reasoning involves making a general conjecture based on specific cases by looking at patterns and recognizing properties. Additional evidence may support a conjecture, but does not prove it. Draw a pair of intersecting lines, measure and record the opposite angles as shown. What conjecture can you make? All right, so let's do this right now. Go here, here. Let's see if I can find my guy here. Here it is. So I'm going to move him. Oh, no, shoot. That's not supposed to happen. Move him. Come on, buddy. That was shrink him. That. Here. Okay, so let's go this up to here. Okay, so if I measure, all right, this is actually going to work as well as it's a mess, but whatever. Okay, so looking at this angle right here, how many degrees is that angle right there? 60 degrees. Okay, so I go over here, I write 60 degrees. What is the measure of this angle right here?
60 degrees.
60 degrees. All right. So now if I look at these 2 angles right here, this one and this one, what is the measure of this one going to be? 130. You got it. How come? 120.
Because 120 and 60 at 180.
Right. Awesome. Okay. So this is a straight line right here. The measure of a straight line is half the measure of a circle. Because if you take the diameter of a circle and you split it, which goes through the radius or through the center of the circle, half that circle has a measure of what in degrees? 180. So therefore, a straight line has 180 degrees. So if I know that this is 60 and I know that this is 60, I can then deduct or make a conjecture that that's got to be 120. What does the measure of this got to be? 120. So what does that tell us about vertically opposite angles then?
They're the same.
They're the same. So based on our work just now, these 2 angles are the same. They're vertically opposite. These 2 angles are the same. We have created a conjecture that says vertically opposite angles are equal. Okay? That is what we call inductive reasoning. So that's one way to do that. The second way to do that, or look at it, is to assess a pattern, okay? And we somewhat assess the pattern there, but we're going to look at this pattern now. So I've got 1 plus 3 is equal to 4. 3 plus 5 is equal to 8. 5 and 7 equals 12. 7 and 9 equals 16. Okay. Examine the pattern in the addends and their sums. What conjecture can you make?
Each of them go by 4.
Which?
The sum.
The sum, okay? Now, what has created the sum to equal 4, though? Like, or equal a number that goes up by 4. What are we adding together?
2 of each side.
Two to both numbers.
Odd numbers.
Okay, so let's start with that. Okay, you guys are all around it. 1 and 3, consecutive odd numbers, yes or no?
Yes.
Yes. 3 and 5, consecutive odd numbers?
Yes.
5 and 7, consecutive odd numbers. So if I add 2 consecutive odd numbers, not only does this go up by 4, but would you not say that all 4 of them are divisible by 4?
Yeah.
So what the conjecture might be, if I add 2 consecutive odd numbers together, I'm going to get a value that is divisible by 4. Okay, so let's try it and let's see. Give me 2 consecutive odd numbers. Larger numbers.
17 and 19.
17, 19. 17 and 19 equals
36.
36. Agreed. Okay, 36 divisible by 4.
Yeah.
Okay, 2 more. Go ahead.
33 and 31.
Divisible by 4? Yeah. Okay. So one of the things that you're going to have to do over the next few days is take patterns like this and go through it and try and disprove your conjecture. So my conjecture, now this is where it's going to get a little bit squirrely, but I'm going to do this and I'm going to show you how this proves that it's done for every number. Now this is the part that you're going to have to do a little bit of this, but not a lot of this. And that's this. All right. First of all, how do I make any number? How do I make an even number? So if I take a value, how do I make it become an even number? What do I have to do to it?
Add.
What?
Add times.
Okay. Which is it?
Add 2 consecutive numbers.
No. Just a number. Okay. Let's take the number 3. What do I do to it to make it an even number?
Add 1.
Add an odd number? Add 1? There's an easier way to do that. What is it? What does every even number have in common? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. What do they all have in common?
Divisible by 2.
Yes, bang. Divisible by 2. So if I multiply any number by 2, I make it even. Yes? 3 times 2.
6.
5 times 2.
2.
10. 12 times 2.
24.
Still even, right? So no matter what I do, whether it's an even number or an odd number, if I multiply it by 2, it becomes an even number. Yes? Okay? So to make an odd number now, I'm going to make that number even, and then I'm going to add 1 to it to make it odd. So think about it. 3 times 2 is?
6.
Plus 1?
7.
7. 12 times 2 is?
24.
Plus 1?
25.
25. So I am creating an odd number. Now there is a reason to do this, and that's right here. I'm going to say that if I go 2n plus 1, that's an odd number. Yes? And I add it to the next odd number, which would be that. Okay? So 2n plus 1, I times any value by 2, makes it even. I add 1, that creates an odd number. The next odd number after that value is 2n plus 3. because you're going to add 2 to that number, right? So just think about it in terms of this. N is 1. Okay, so N is 1.
Excuse
2
me for
times
the
1.
interruption. Xander Tucker to the office, please. Xander Tucker.
2 times 1 is 2. 2 add 1 is 3. 2 times 1 is, add 3 is 5. Okay, so I've got that so far. All right, odd number added to the next odd number in the counting. Okay, so I'm adding 2 consecutive odd numbers together. I'm going to play with this for 1 second, and then I'm going to see what it equals. Okay, so I'm going to get rid of my brackets. Hello. Oh my gosh. Okay. I know. Thanks, buddy. Okay, I gotta go for a sec here. Okay, 2n plus 1. Get rid of the brackets. 2n plus 3, like this. Okay, add the like terms together. What's 2n plus 2n?
4n squared.
No, oh, I don't add the values. Just add n's. 4n. 1 plus 3 is 4. Okay, now we're going to factor this. Actually, do me a favor. Go downstairs into the staff room. In my jacket pocket are my keys. Grab them and give them to Gabby's grandpa. They're right now. Okay. Okay. So I'm at 4n plus 4. All right. That's what it equals. Now, watch what happens here. Is there a common factor between 4n and 4? Yeah, what is it? 2, or what's the higher one? 4. So I'm going to factor a 4 out of here. So I get this. Now, it does not matter what n is anymore. If I add 1 to it and times it by 4, that means it's divisible by 4. Okay, so let's use an example. I used n equals 1. And I got 3 plus 5, yeah? Okay, n is 1 here. 1 plus 1 is? 2 times 4 is? 8. That's what we got there. Okay, let's try this again. N is now 2. So let's go back to the beginning. 2 times 2 is? 4 plus 1 is? 5. That's right there. 2 times 2 is? 4 plus 3 is? 7. N plus 1, so 2 plus 1 is? 3. 3 times 4 is? Right there. So what I have done is I have taken my little trial of patterns, and I have proven that this will work for absolutely any number. There is nothing to prove this incorrect. So eventually we are going to get into this, but not for 3 or 4 days. But that is where it's going to get to. Now, it's not going to be that complicated. All right? Good. Thanks. Okay. All right. So that's patterns. I want you to flip over to page 8 now. So we're going to go through the first 3, and then you're going to get time to work today. This one's kind of neat. A conjecture can be supported or disproved with further evidence. So looking back at this conjecture right here, I could have gone through this and I could have found every consecutive odd number known to mankind and added it together, and it would have proven that it was divisible by 4. And I know that because when I let a variable represent any number, it worked. But it's not always going to be the case. There are going to be moments where that conjecture that you make isn't always true. So it's up to you to prove it or disprove it. And really, you're trying to disprove that conjecture all the time, because the pattern should be what it is until you can prove it wrong. Okay? So here's an interesting one. I like this. Look at that picture on that page, and I want you to tell me, are the horizontal lines in this diagram straight or curved? Go. Are the horizontal lines? That's the ones that go across. That's one. I knew you were. You looked at me that way. Are those horizontal lines straight or curved?
Straight.
Anybody want to go with curved?
Straight.
What do you think?
They look straight.
They look straight? I don't know, they look kind of curved to me.
Yeah.
Nobody wants to go with curved? Okay. I see it as curved too. What is the correct answer though?
Straight.
They are straight. So what is it about that that makes them look curved?
All the lines. Illusion of the lines sticking out.
Okay? Possibly. Possibly. What else should give it away?
The black dot.
The black dot. The fact that that dot is a circle leads you to think that it has to go around the circle. Maybe. I don't know. So how do you prove that they are straight? A ruler. Simple enough. Use a ruler. Check it. See if it's straight. They are straight. So a conjecture. I conjectured that the horizontal lines are straight and that the apparent curvature is an optical illusion caused by the diagonal lines. So somebody had said that about the lines. Correct. The diagonal lines do lead you to do it. I put a ruler alongside each horizontal line. The lines were indeed straight. To verify my conjecture, I measured the distances between the horizontal lines. The distances were equal, so I knew that they were also parallel lines. So those two straight lines were also parallel to each other because the distance between them didn't change. Okay? All right. Now, here's one of those ones where we are going to prove right or wrong. 1 over 1 plus 1 over 2 is equal to 3 over 2. Not even close. 3 over 2. Okay. There's pattern number 1. 1 over 2 plus 1 over 3 equals, what is it? It's 5 over 6, isn't it?
Yeah.
Okay. 1 over 3 plus 1 over 4 is 7 over 12, yes?
Yep.
And 1 over 4 plus 1 over 5 is 9 over 20. Yeah.
They have 1 over 5.
1 over 6.
Oh, it was 1 over 5 and 1 over 6? All right, 1 over 5 plus 1 over 6 equal to 11 over 30. All right. Somebody volunteer. I want the next in the pattern. Who's brave enough to guess? Cash. Knew it.
Well, the top will be 13.
Hold on. What are we adding?
1 over 1 plus 5 over 1.
What are we adding next? You tell me what we're adding next.
Well, the bottom are common multiples of 30.
That'd be
Okay.
1 over 5 plus 1 over 6.
No, we already got that one.
So it'd be 1 over 6 over 1 over 7.
And 1 over 7. And that is equal to
1330.
13 what?
Oh, 1347.
Do we agree with Cash? Who doesn't agree with Cash? Apparently they like you. Thanks for the scaredy one of them. Okay. What's the next one?
1 over 7 plus 1 over 8.
1 over 7 plus 1 over 8. Tosh, finish it.
15 over 56.
Okay. So how do we make a conjecture out of that? See, this is the part that is, you're going to read a lot of the answers in this book. You're going to want to, you know what to do, but how do you say it? So that's where the answers in the back of the book are going to help you, except you don't have them yet because you have no books. Okay, except for Zach. All right, so go ahead. You talk to me.
Well, the bottom equals the top. Like if you add them together.
Okay.
The bottom denominator. You know what I mean?
Yeah, I do.
So if you have two numbers that like, I don't know how to explain it.
See, that's what I mean.
Two numbers on the
You-
bottom go on the top of the next one, and then you add
And you just multiply them.
Yeah, you can.
Okay.
Isn't it?
So, two consecutive fractions. All right, let's start with that. Two consecutive. Consecutive is a word you're going to use quite a bit. Two consecutive fractions. as long as 1 is in the numerator. Key 2, that's also important. It has to be a 1 on the top. Okay? So 1 over 7 plus 1 over 8 is equal to, add the denominators together to get that numerator, and then multiply the denominators together to get that denominator as your sum. Make sense? Okay, so let's try this. 1 over 10 plus 1 over 11. 1 over 10 plus 1 over 11.
21 over 110. Or 11.
You read the first one.
110.
21 over 110. Okay, so again, because you have to do this a little bit, I'm going to show you this one more time. 1 over n plus 1 over n add 1. So what should be on top of this?
And 1.
N plus 1.
N. So I got to add this to this, yeah?
Will just be n.
No. What's n plus n?
2n.
2n, right? Add an apple to another apple, I get 2 apples. So 2n, add 1 on top. Yeah? Bottom?
2n squared plus 1
Close. Get the second part right.
Plus 1n.
Yes. All I'm doing is taking this times these right here. So n times n squared, n times 1, n. So that's it. Again,
Is that actually plus on multiple?
where you at?
You said multiply.
Yeah, I multiplied this times this to get the bottom. Yeah. The top part's the plus. Okay, now I'm going to show you how this works. Again, we're going a little bit beyond what we need, but that's okay. So I'm going to add those two together on the left side. What do you do to add fractions together? What do I need? Common denominator. Now, this goes into 3 months from now, we're going to have to do this. So I'm going to do it for you right now. I need a common denominator between n and n plus 1. All right, I'm going to do something else while I'm on a tangent here. What's the common denominator between those two right there? 6. So to get 6, I am looking at the value that both of those go into, the lowest value preferably, right? Or if I'm not sure what that lowest value is, how do I find the common denominator between the two? Yes, very good. Thank you very much. I can always multiply the denominators together. It may not give you the lowest common denominator, but it'll always give you a denominator that is common. Okay? So I'm going to multiply those two together. On the bottom, I have this. Okay. What do I have to times n by to get that right there?
1.
Nope. Close though. I need to get that to look like this. So what am I multiplying that n by?
N plus 1.
Yeah. N plus 1. So if I have to multiply the bottom by n plus 1, I also have to multiply the top by n plus 1. Okay. What do I have to multiply n plus 1 by to get to this?
N.
N? There's what I get right there. So far, so good? Okay, all I did, so over here, if I was to add these together, what do I times, here's my denominator, right? What do I times 2 by to get to 6? 3. And what do I times 3 by to get to 6? 2. So I end up with 5 over 6, yes? Okay, so I end up with this. So now I'm going to collect the like terms. N and n make 2n, and let's add 1. And then down here, I have n squared plus n, which is that. Okay, again, not something that we need to do anytime soon. But what I have just proven is that this will work for every one of these in that pattern. I have proven the conjecture correct. Whatever the conjecture is that he said, I've proven it correct. So 2 consecutive numbers, 2 consecutive fractions with numerator as 1. Add them to get the numerator, multiply to get the denominator. All I'm probably looking at you for right now, can you recognize the pattern and write the next few out? That's what we're looking at. All right, one last one. Page 10, and then you're off and running. Using reasoning to find a counterexample to a conjecture. So what you're trying to do is find a counterexample to prove your conjecture is incorrect. You're trying to disprove your conjecture. All right, so we're going to start with the pattern, and you tell me when you think you have the pattern figured out. Okay, now I'm going to do this over here. Okay, so what conjecture can you make about the pattern? How can you check whether the conjecture is true? And let's go through it. All right, so somebody tell me, without use of a calculator, 14 times 11. What is it?
444.
You say
No.
444?
No.
No? Okay. Sorry, go ahead.
154.
154. 154. Agree? Disagree? Agree? Okay. Test Sarah again.
Or 242. Shut up.
Hands up if you have no clue how she's getting that.
That was a bit good.
You know what you're doing? Put your hand up. Maddox. No, you don't know what you're doing. You'll be fine, trust me. Okay. So all right, so I want you to look at what you're multiplying and what the solution is and see if you can figure this out. Now remember, there is some sort of pattern here that we are doing. So look at the numbers that you're multiplying by 11 and what the sum is.
Isn't there like you see on 11 times 11, it's 121. And
They're going by 11.
Yeah, it goes up by 11.
Well, in that case, yes,
And not
100%.
on the end of
But how
both
does it work
sums-
for these two, though, is what I'm saying.
on the end of both the sums, you can kind of see like 12 and then 26 and then 43. Like on the end.
You're close. You're on the right track. Okay, so let's start with that. He's done a great job. Look at the first and last number of the multiplication of the product. What is the first and the last number of the product?
No. I guess.
1 and 2.
No, you just add them to get them.
Okay, and now he's got the second part of it. What's the second part?
You add the two numbers together.
Okay, so let's do this. Write that down on a piece of paper. What is the answer? Just write the answer down.
I go in my head.
Get it on the paper.
You split it in.
Kaylin, Are we lost?
I kind of done it.
Okay, what's your number?
Well, because I just go 53 times 10.
No, don't be like that.
No,
All that stuff they taught you in the elementary school. Gee whiz. Okay, Kaylin. What number are we multiplying by 11? 53.
5 and 3 going
Exactly.
They go on the outsides. What goes on the insides?
5 plus 3.
Now, they're a lot of help. You kicked their butts all last year, and now they're a lot of help.
New year, new me.
Add them together. Let's hope so. 583. You see the pattern? Whatever you're multiplying by 11, okay? The numbers go on the outside, and the sum goes on the inside. So that's the conjecture we make. Whatever number I multiply by 11, those go there, and the middle is the sum. Now, we need to prove that that works all the time. So give me a number, a 2-digit number to multiply, and again, I have to preface that. It has to be 67. Do we have to go there already?
He told me to say it. That was not me. Anyways, 41 then.
6.7.
All right, so let's do it. Kaylin, write it down. What do you got in your paper?
451.
Is that the correct answer? Yes, it is. 451 is the correct answer. All right, now we have to disprove this somehow. Okay? So I'm going to have you do this. What is the correct solution here? What is the correct solution? According to our pattern, what is the correct solution? What are the numbers on the outside, Maddox? 6 and 8. Good. And what goes on the inside, Maddox? Okay. Which is?
14.
Okay. Is 6,148 the correct answer for that?
No. Wouldn't you have to, like,
Put him on the
add
outside
the 1 to
instead.
the 6?
No,
You put the 1 before the 6 and the 3.
you don't. The correct answer to this does not work with our pattern. If the numbers add to give you a two-digit number, so if the 2 digits add together to give you a 2-digit number, this pattern doesn't work. It only works for single-digit sums. So let's just look at, we'll start here. 53 times 11, 54 times 11, and 55 times 11. So let's put those down. So what's 53 times 11?
583.
583. What's 54 times 11?
594.
594. And what's 55 times 11?
Can you not do it? Right there.
605.
Right. Okay, because if you add 11 to this value right here, what do you get? 605. That does not support our pattern. So that is a way in which we just disproved that pattern is correct for all. It is correct for any number that has a single-digit sum. So you can preface that too. You can say that if I multiply a 2-digit number in which the sum of those 2 digits is a single-digit number, then that pattern would work. So that just means you have to change your conjecture. What are you doing? Okay. Starting on page 5 today, I want you to get working through all of that.
Can you work with a partner?
No, you can work on your own for right now.